Not funny, Chris.
I'm not funny, so you should be used to this.
Okay, so this is something that you wrote down yesterday. Do you agree? Okay. You are going to get a statement, and our process is going to be to show that it's true for the first, and then we need to show that K implies K plus 1. Okay? If that's true, then we can say that the statement is always true. All right, so you're going to see some N's and some K's. All right, you kind of noticed that yesterday. This statement is going to be given to you in N's, and then in your proof, we're going to change them to K. So N is going to be representing all of the natural numbers, and K is going to be representing a specific number. And K plus 1 would be the next one. Okay? We kind of talked about that domino effect yesterday, right? And you don't need to write this down because this is just different words than up here. We talked about that domino yesterday. If we can show that 1 is true, and that any domino is going to knock over the next domino, and 1 knocks over 2, 2 knocks over 3, 3 knocks over 4, 4 knocks over 5. Okay? So, with those three things, those two things, showing 1 is true, and then showing K makes K plus 1 true, then we can knock over all of our dominoes. Okay? So these are the steps that I'd like to see. The first one is that you're going to physically plug in 1 to make sure that it is true for when you plug in 1. Now, all of these are going to be like sum formulas. We are going to prove shortcuts for summations, okay? So when you see S, S is like the sum of some pattern, okay? Which is why we're talking about it in this chapter, because we've been doing sequences in series, or we at least did before we did probability. Okay. So in step 2, you are going to assume the formula is true for K. And you will literally write the word assume, and then you're going to write the formula with K's instead of N's. That's all you're going to do. Okay, then using algebra, we are going to show that S sub K plus 1, so the sum of the K plus 1 terms is true by this. I'm going to let you write it down, and then I'm going to explain to you what I mean by that. Okay, so we're going to have a sum formula, yes?
Why should you K plus 1? Why is that K?
We have to change, okay, so like I said earlier, like when we say N, we're talking about all the natural numbers. When we change it to K, we're talking about a specific place in the sequence as opposed to all of the numbers in their entirety. So we're like picking a place, but we're not calling it a number. Like if I pick any sum k, and then the next one is k plus 1. So it's like choosing 2, and then the next one would be 3. But instead of calling it 2, we're calling it k, because it could be anywhere in the sequence.
So n is the 2.
N represents all the natural numbers. So like k is like me choosing a domino. If I choose any domino, does it make the next domino tip over?
So n is like all the values.
And it's all the dominoes. Does that help? Okay. So when we assume the formula is true for k, we're going to have a sum of k terms. Okay? Well, if we look at the sum of k plus 1 terms, that's just the sum of the k terms, and then we add one more term to it. We add the k plus 1 term. Does that make sense? Okay. So we're going to do 2 examples so I can show you what this looks like. Okay. What you worked on yesterday, remember that assignment that took you like 2 minutes to complete? Okay. What you worked on yesterday, that's where we need to end. Okay. So you're going to know what the last step is in your proof before you do any of the algebra. And your goal is going to be to get to that step that you wrote out yesterday. Okay, so what I'm going to have you do is I want you to go ahead and write down this S of n formula. Okay, so this is basically saying that if we add up all of the odd numbers, it's the same as n squared. Okay, so if we take the sum of the sequence 2n minus 1, that's what this is, the sequence is 2n minus 1, then it will be n squared. Okay, so what's our first step? What's our first step? Put your notes, what I tell you. What was the first step?
Prove it to be true for 1.
Prove it to be true for 1. So S of 1 is 1. Is that the same as 1 squared? Okay. 1 equals 1, so we're good. Take the first term. Is it the same as when you plug in 1 to the rule? Okay. Then our second step, we're going to choose any sum k. So we need to assume that S sub k equals 1 plus 3 plus 5 plus 7 plus all the way to 2k minus 1, and we want it equal, we want to assume that that equals k squared. Okay, here's what we do next. We're going to then look at the k plus 1 sum. Okay, well, the sum of the first k terms is 1 plus 3 plus 5 plus 7 all the way up until 2k minus 1. So if we're going to add one more term, then instead of this being k, we're going to make that k plus 1. We're adding on one more term because it's the k plus 1 sum. So I just took this rule right here, the 2n minus 1, and I put k plus 1 in there instead of k, because we're adding on one more term. Now, we don't know what this equals, okay? We don't know. We can't write equals blah, blah, blah. However, we know what we want it to equal. If the k sum is k squared, what do we want the k plus 1 sum to be?
K plus 1 squared.
K plus 1 squared. So what I'm going to do is, way down here at the bottom, I'm going to write that the k plus 1 sum is k plus 1 squared. And if we could get our algebra to lead us to that, then we have completed our proof. Okay? We are showing that the k sum implies that this is true. Yes.
Like on the part where it says then, why do you add the second to k plus 1? Like, why wouldn't you just do the plus 1 on the first part? Do you know what I mean?
Well, because the k plus 1 sum has the sum of all of the k terms, and then we have to add the k plus 1 term. So it still has all of those numbers added together. We just have to add an additional term to it.
So you have to add a whole new k, like you can't just add the 1. Like you have to put k plus 1.
Yes. Yes. It's kind of like if we think about the fourth partial sum, the fifth partial sum, we just add the fifth term to it.
Okay.
All right, so let's rewrite that. This is the same thing as 2k plus 1. Do you agree? Okay. Now, I'm going to underline something in red. What do we know about what I just underlined in red? It equals k squared. This is the sum of the first k terms, and we know that it equals k squared. So what we can do is we can write it as k squared plus 2k plus 1. That was intentional, okay? That will happen every time where you can replace the s sub k sum with whatever you assumed that it was equal to. Now, k squared plus 2k plus 1. Think we can factor that? Oh, k plus 1 times k plus 1, which is the same thing as k plus 1 squared. We got there. Okay, just like with any other proof, we need to conclude it. Okay, what did we just show? So I'm going to write, therefore, S of n is true for all positive integers. Okay, in other words, you don't have to write this, but I want to explain to you what we just showed. We just showed that 1 plus 3 plus 5 plus 7 all the way up to however many odd numbers you have is the same thing as Yeah. Well, see, our sequence is 2n minus 1. So the first term is 1, and the second term is 3, and the third term is 5. Does that make sense? So if we add up the first 3 odd numbers, it's the same as 3 squared, which is 9. Okay. A lot different than your geometry proofs, yeah? Yeah. You guys were a little nervous, weren't you?
I'm not sure there's two.
This is a lot more algebra based. Woohoo. Okay, one more. Then I'm gonna make you do one yourself. So this is saying if we take the sum of the sequence 3 plus 2n, it would be the same as n times n plus 4. So our proof. First step is to show that it's true for S of 1. What's our first term? 5. Is that the same as when we plug in 1 for n? 5 equals 5. We're good to go. Number 2. What word do we start out with? Assume. It's like the one time you get to assume in math. It's great.
Why do you have to say assume?
Because we don't know for sure if it's true or not. So let's assume that it's true. Doesn't make the next one true. Great question. Okay, assume that it's true for S of k. And we want to consider the k plus 1 sum. As we've talked about, the k plus 1 sum is the k sum. Plus the next term in the sequence. So just plug k plus 1 into the sequence for the next term. Do not make that equal to anything. We don't know what it equals, but we know what we want it to equal. What do we want it to equal? If the k sum is k times k plus 4, what do we want the k plus 1 sum to be? K plus 1 times k plus 5. K becomes k plus 1. K becomes k plus 1. So now we have k plus 1 times k plus 5. That's the same thing that you practiced yesterday. All right, so let's rewrite this. We have 5 plus 7 plus 9 plus 3 plus 2k plus 3, no, 5 plus 2k, correct? Do you agree? All right, help me out. What is 5 plus 7 plus 9 plus ... all the way to 3 plus 2k? K times k plus 4. Guess what, guys? That's going to happen every time. Every time. Okay, now it's a matter of figuring out how to get our algebra from there to where we need to be at the bottom. Thoughts? Okay, let's distribute. K squared plus 4k plus 5 plus 2k. We're eventually going to need to factor, so combining like terms would be a good idea. K squared plus 6k plus 5. Does k squared plus 6k plus 5 factor to k plus 1 times k plus 5? Right? You don't even have to factor. It does it for you. Okay? So we got there. Awesome. Therefore, S of n is true for all positive integers. All right. Okay. Couple things before I let you work. We have 20 minutes. You have to get number 11 done before you leave. Have to. And you have to call me over for me to check it over. I want to make sure that you're doing the process correctly. Now, make sure that the k plus 1 sum looks consistent to the k sum. If there's a fraction in the k sum, there better be fraction in the k plus 1 sum. Okay? It needs to look the same just with the k plus 1 plugged in. I believe there are 5 problems you need to do. Are they all bolded? Okay. There's 5 problems. Okay? You're going to work on number 11. You're going to call me over. I'm going to look it over. And then you're going to proceed to number 12. And you're going to work until the bell rings.
642.
There.